Welcome to the Explainer. Let's just dive right in, shall we? When we hear the words South Asian summer monsoon, most of us immediately think of, well, weather, heavy rain, dark clouds, maybe battling the wind with an umbrella. But what if I told you that the monsoon isn't just a weather pattern? It's actually a colossal, geologically engineered planetary machine. Seriously. Today, we're unpacking the massive thermodynamic engine that drives the world's biggest storm. We'll look at how it was literally built by colliding continents and how human activity is currently kind of messing with its control panel. So why does this matter right off the bat? Well, 2 billion. That's the number of people living downstream who rely absolutely directly on the water pumped out by this massive atmospheric engine. The river system is fed by this setup, the Indus, the Ganges, the Brahmaputra. They support agriculture, economies, and literally life itself for almost a quarter of the global population. This is, hands down, the most important water tower in the world. But to really get how this machine works today, we've got to rewind the clock. Because the story of the world's most powerful weather system doesn't actually begin in the sky. It begins deep within the Earth. Our story starts about 50 million years ago, right after the ancient Gondwana supercontinent broke apart. Picture this, ancient Indian landmass. It was basically moving at a geological sprint, consuming up to 8,700 kilometers of oceanic plate as it raced northward through the deep blue void of the ancient Tethys Ocean. Eventually, though, it had absolutely nowhere left to go, and it slammed head-on into the massive Eurasian plate. Now, when two continental plates of that size collide, neither one is willing to just sink into the mantle. Imagine taking a heavy, thick rug and pushing it across a slippery floor until it hits a solid wall. With nowhere else to go, the fabric has no choice but to buckle, fold, and thrust violently upward. That is exactly what happened to the Earth's crust here. It violently crunched and folded, breaking the flat plane and pushing jagged rock miles into the sky. This established the towering Himalayan wall and the massive Tibetan Plateau sitting right behind it. But this epic collision didn't just build the roof of the world, it built an atmospheric engine. The really crucial takeaway here is that this monumental continental collision gave us the physical framework for the Asian monsoons. I mean, think about that. The rock beneath our feet literally dictates the sky above us. Let's break down how this creates what atmospheric scientists call the thermal engine. Because the Tibetan Plateau sits over 4,500 meters high, its barren soil sits right in the middle of our atmosphere, absorbing intense solar radiation directly. As it heats up, it warms the thin air right above it, acting exactly like a colossal solar-powered chimney. And as that elevated landmass heats the air column, it creates a massive area of low pressure, a vast vacuum about 9 kilometers up in the sky. This high-altitude void acts aggressively, sucking in moist, energy-rich air and pulling it northward all the way from the Indian Ocean. But science is rarely a completely closed book, and there's actually a really fascinating debate about what primarily drives the monsoon. Is it mostly this thermal engine, that solar chimney effect of the high plateau we just talked about, or is it driven by something called orographic insulation, where the mountains are simply acting as a giant mechanical barrier? See, while the plateau is pulling in air, the mountains themselves serve as a fundamental mechanical barrier. Just imagine these rigid, sharp winds of freezing Siberian air sweeping southward. As they strike the towering peaks of the Himalayas, they just shatter and deflect away. The mountains act exactly like a heavy, sealed winter door on your house, physically blocking that freezing winter draft from coming inside. Because of this massive shield, the Indian subcontinent is perfectly insulated, which lets it trap heat and moisture like a warm, humid greenhouse, perfectly setting the stage for deep, systemic tropical storms. Whether it's driven by the chimney, the winter door, or, likely a combination of both, the output of this machine is just spectacular. 11,872 millimeters. That's the average annual rainfall of Mawsynram, a cluster of villages in northeastern India. It is officially the wettest place on Earth. To put that completely wild number into perspective, that is almost 39 feet of rain in a single year. And the sheer violence of this weather system? It's staggering. Get this, on June 17, 2022, Mawsynram received 1,003.2 millimeters of rain in a single 24-hour period. That is over 39 inches of rain in one day. So how does this specific geographic spot manage to squeeze so much water out of the sky? Well, it all comes down to geographic mechanics. As our planetary vacuum pulls all that saturated air up from the sea, the wind inevitably crashes into sheer vertical cliff faces, like the Khasi Hills. Forced abruptly skyward, the air rapidly cools. It's literally like taking a soaking wet sponge and suddenly squeezing it with both hands. The rapid change in altitude forces the air to violently wring out almost all the water it holds, all at once, creating an instant, continuous condensation machine. To ground all this grand science in human reality, just imagine living inside that squeezed sponge. During the core monsoon months, Mawsynram is perpetually inside a cloud. Horizontal visibility drops below 50 meters for weeks at a time. To actually survive and work in this extreme microclimate, locals rely on brilliant traditional engineering. Kunups. These are body-length, turtle-shaped rain shields woven from bamboo and waterproofed with banana leaves. They let people walk hands-free through just relentless, zero-visibility downpours. So we've got this ancient, finely tuned, 50-million-year-old planetary machine. But what happens when we start tampering with its settings? Because today, human activities are actively shifting the climate future of the monsoon. We're seeing a warm ocean, warmer land trend, which forces way more moisture into the air. But at the exact same time, we're pumping out aerosols that shield the sun and stabilize the atmosphere. It's creating a super complex tug-of-war right up in the sky. We are aggressively pulling the levers of this machine in completely opposite directions. On one side, greenhouse gases are warming the system, which theoretically increases rainfall. On the other side, sulfate aerosols from pollution act like a giant mirror, reflecting sunlight and actually reducing rainfall. In fact, aerosol pollution currently masks the greenhouse warming effect by over 60%. And meanwhile, black carbon is just absorbing heat directly in the atmosphere. But perhaps most concerning of all is the plateau itself. We are seeing a rising surface pressure trend over the Tibetan Plateau, entirely driven by a warming climate. Studies show that even a tiny 1 or 2 degree change in the soil temperature of the plateau can dramatically alter the temperature gradient all the way down to the Bay of Bengal. Think about it. If we change the temperature of the solar chimney, we alter the thermodynamic fuel of the entire system. That means severe droughts in some areas and catastrophic, unprecedented flooding in others. Which brings us to our final and really most critical question. We've seen how colliding continents built this magnificent, life-giving engine over millions of years. But what actually happens to 2 billion people when human activity fundamentally alters the thermodynamic fuel of a 50-million-year-old planetary machine? It is a highly delicate balance that we all rely on, and we are modifying the blueprint in real time. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time.